So your 5-minute review on momentum and momentum concepts and terms. The first thing is we should define what momentum is. Momentum is mass times velocity. Since velocity is a vector, that means that momentum is also a vector. The units are Newton seconds, and one of the things about momentum is when you think Newton seconds, Newton force, seconds time, most people don't really care about the momentum of an object. Most of the problems you're going to see are going to deal with the change in momentum of an object, which we call impulse. So that's actually the next slide, is impulse, which is known as the change in momentum, delta P. Usually is the velocity that changes, but there are some cases where that is not true. For example, is the two examples that I've just put on this screen involving the train and involving the ship. Now, as I pointed out, based on the units of momentum, Newton seconds, that means impulse, J, is force times time. Now, this is where momentum and impulse get tricky, because impulse is also delta P. So if I want to know what's the impulse on a 5 kilogram object that speeds up from 4 meters per second to 20 meters per second, I'm not going to use force and I'm not going to use time. I'm going to use the mass and I'm going to multiply by the change in velocity. 4 to 20 was a change in velocity of 16. So when I take the 5 kilogram mass and multiply by 16, I get 80 Newton seconds of impulse. I could now say 80 Newton seconds equals force times time. So if I found out that, hey, the force applied was 20 newtons, all right, it took 4 seconds to do this. Newton's third law plays a huge role in the conservation of momentum and how impulse works. So let's run through this together. So you have two objects that collide, or you could think of it as one object explodes and becomes two objects as they push off of each other. By Newton's third law, the force has to be the same. The time also has to be the same. It is impossible for object A to make contact with object B without object B making contact with object A. Therefore, since impulse is force times time, they would have the same impulse. And since impulse, by definition, is a change in momentum, the two objects would have the same change in momentum. Now, if we think about a bug splattering on the windshield as you drive up north, your car is the large object, the bug is the small object. Your car will have a negligible change in velocity, and the bug would have a dramatic change in velocity. Now, the change in momentum between you and the bug, your car and the bug, would be the same. And the reason why is because the car is so massive, it has a small delta V, whereas the bug is so small, it has a massive delta V. But ultimately, since they have to exert the same force by Newton's third law, be in contact for the same period of time, they have the same impulse and therefore the same change of momentum. The conservation laws that come out of this is the momentum before the event has to equal the momentum after the event. There's an exception to that, and that is that there's an external force. An internal force cannot change the momentum of the system. It can change the momentum of individual pieces of the system, but it cannot change the momentum of the system as a whole. Now, this chart is on the momentum PowerPoint that is on Moodle. This is a good one to take a look at, or just pause the video and screenshot it or write it down or whatever. This shows you how total energy, mechanical energy, and momentum are conserved across the three types of collisions. An elastic collision, by definition, means all the mechanical energy is stored. Well, what is the mechanical energy? The mechanical energy is, in this case, kinetic energy. Inelastic collisions, which are far more common and actually are virtually every collision you would ever see with your eyes, has to be inelastic or totally inelastic. The mechanical energy is not conserved. So where do the elastic collisions happen in the real world? They happen at the atomic level. Now, it is possible to do a problem with an elastic collision. You could see something like billiards, for example. The billiards as the pool balls collide. Those are pretty close to an elastic collision, but not quite. Next review will be rotation.